Guys, the next thing that I learned is the law of total probability, and let's start discussing about it. Okay, you want probability of A, but it's hard to compute directly. Instead, partition the sample space into exhaustive, non-overlapping cases and find the value of probability of A within each case. Then just add them. So it is the probabilistic version of consider all possible scenarios. Mechanically, if we see this, it converts a hard and conditional probability into several easier conditional ones. Okay. So this slide I just now told to you. Next, moving on forward, the geometry of total probability is like A is equals to A intersection B1, union A intersection B2, union A intersection B3. As, as you can visualize it from in this from the slide. Okay. So now we verifying the like events B1, B2 till Bn from a partition of the sample space if exhaustive is like B1 union B2 union till Bn is equals to sample space. They cover everything. Then comes mutually exclusive means B1 intersection B2 is phi. That is the second rule that it should follow. And the third is positive probability. Probability should become must come as positive only. Next thing is like law of total probability. But it says that just sum over all the partitions means that this is saying the probability of A given we are in scenario of BI and this says that probability of being in scenario BI. Okay, this is the weight and now this implies the product implies that it is the multiplication rule which implies that A intersection BI. Now, what is the probability of A which we want to get and what it is calculating? It is the summation symbol, so it's calculating sum over all the partition probability of A because A intersection BI means A intersection B1, A intersection B2, A intersection B3 until how many B parts are made. These all are mutually exclusive and their union will be equals to A. Now, if you want proof in one line, okay, how I can explain here? Let's go down here. It will be, yeah, see, this formula. This means integrating all the A, integrating all the parts. Like, it's the continuous version. Partition replaced by density, where fx is the density of x. Same idea, integrate over all scenarios weighted by their density. Now moving on to top here. So this is just an example to show that total of probability and then when to deploy architecture. Okay, when you want to compute A, when you want to find probability of A, it is hard to compute, just break it and find in partitions and these partitions should follow three rules that I already told you. Now, the failures where this we can make what we say problems and where we can go wrong. So partition must be exhaustive first of all and mutually exclusive. Second is weighting by probability BI is mandatory. Okay, what is BI? All the small parts of B, B1, B2, B3 until Bn. Okay. Then choosing the wrong partition is the third mistake we can do. The partition must be chosen so that probability of A given BI is actually knowledgeable. Like it is actually simpler and you can get it. A partition that still makes probability A given BI hard gives you nothing. So good partition usually comes from casual structure of the problem. Next thing is confusing with the bias. Law of total probability computes probability of A forward from the causes to effect. Okay, Bayes theorem is the next topic which we will cover, and Bayes theorem goes backward from observed effect to cause. Okay, LTP is actually the denominator inside the base. Now, next mistake which we can make is like infinite partitions. The law extends to countably infinite partition, but you need the series to converge. Okay, in continuous cases, you use the integral form. What we sometimes apply the discrete sum to continuous setting incorrectly. So just noted that. Okay. Now, why we are doing this, why we need to understand this topic is like it is used in machine learning in a way like marginalizing out latent variables in generative models like there will be a term called over latent z. This is like exactly LTP. The ELBO is something in VAEs involves approximating this interactable sum. Okay. Now, mixture models also use this thing. Like Gaussian mixture models are the direct application of this total sum of probability. And there's one more topic which will be just upcoming in almost topic 15, like total expectations. Means the expectation of LTP used constantly in it is used constantly in ML analysis. So, okay, I fluttered at the last. I tried to explain. It's okay. So the next topic is Bayes theorem. Uh, we'll make the next video and hope you like the explanation. And I feel that I fluttered at the last. It's okay. If you find any kind of another mistake, just point me out and I'll just note on that. Thank you.